Hello and welcome to this webinar of the Secure and Efficient Data Spaces Project, or SeEDS for short. In this webinar we will talk about what SeEDS is all about and how it works. But first, who are we? SeEDS was envisioned by a team from the Mobile Multimedia Laboratory of the Athens University of Economics and Business located in Athens, Greece, consisting of postdoctoral researcher Yannis Thomas and Nikos Fotiou, PhD candidate Iakovos Pitaras, graduate students Fotios Bistas and Ioannis Barous, and Professor George Silomenos. Our team was assisted by Professor Chris Papadopoulos from the University of Memphis in the United States of America. The SeEDS project is funded by the NGI Sargasso project, which was itself funded by the European Union. We are grateful for their support and would like to point out that the views expressed in this presentation are our own and are not representative of the EU or of the NGI Sargasso partners. First, a few words about the presenters. I am George Silomenos. I am a professor at the Athens University of Economics and Business, or AUEB, and director of the Mobile Multimedia Laboratory, or MMLab. I started working in information-centric networking, which is one of the core pieces of SeEDS, in 2008. I participated in a series of pioneering EU-funded projects on information-centric networking. I have also followed closely the developments in the standardization of decentralized identifiers, or DIDs, and verifiable credentials, or VCs, which are also instrumental in making SeEDS secure. I am the leader of the team designing and implementing SeEDS at the MMLab.
Hi everyone, my name is Christos Papadopoulos. I'm a professor at the University of Memphis. I have been involved with information-centric networking since 2007 as one of the co-PIs or the primary principal investigators in the Named Data Networking Project, which is a project that was funded by the National Science Foundation. I have been active with the NDN project, both in terms of the design and the development for several years now, and I have been contributing both in terms of software and in the architecture design. My role in the SeEDS project is to review the SeEDS design, validate its assumptions, and then provide advice and a little bit of a consulting service to the NDN team to offer my NDN expertise.
Let's start with an outline of the webinar. The first part talks about the vision behind SeEDS, that is, what we're trying to do and why. Specifically, we will first go through some motivating use cases to explain the problems we are trying to solve. Then, we'll outline the SeEDS solution and how it addresses the problems identified. We will then explain the benefits from adopting SeEDS in a wider sense, beyond the immediate problem that it solves. The second part of the talk is more technical, providing details on our actual design and implementation. We will first explain what are the data spaces that the SeEDS project refers to. Then, we'll provide an overview on named data networking, the technology upon which our data space implementation is built. Having set the stage, we will explain how, with message sequence charts and graphs, how exactly we have implemented the operations of data spaces over the named data networking underlay. And we will then describe our privacy preservation scheme, which allows selective revelation of content with strong authenticity guarantees, and of course why this is important. We will close the webinar with a progress report of ongoing work and our plans for the future of SeEDS. Let's start with the first part of the webinar by offering some motivation for SeEDS. Our first use case is a company making wearable devices. Maimon, a company making wearable health monitors such as smartwatches. These devices can generate tons of data as they are always on, monitoring the user wearing them. For example, periodic heart rate readings, logs of your activities such as walking, running, sitting and sleeping, the locations that you are visiting, and maybe interactions with other devices from the same manufacturer. All this data can be used to build a wide range of interesting applications. For example, an application can monitor the user's daily habits and workouts, provide summaries of the workouts, and even suggestions of what the user should do to complete a goal. Another application can look at the vital signals gathered to detect anomalies and prompt the user to seek medical assistance, or simply send the monitoring data to a doctor for analysis. The question is, can we trust a wearable device with data that are clearly private? Actual medical data are clearly private, but so are location data and interaction logs. Ideally, a user should have the tools to decide who can see what data. For example, for medical data, the user could allow emergency room doctors to have access to them without any additional approval. On the other hand, the user could prefer to keep medical data hidden from insurance companies and employers to safeguard his or her privacy. Do existing wearable devices have such capabilities? Our second use case is a company that operates buildings. My Building is a company that manages office or residential blocks, handling maintenance, security, cleaning, or any other kind of service. A modern building is full of IoT sensors, and it is most likely that the company operating the building will have to manage them. These sensors generate tons of data about what is happening in the building. For example, gate sensors log who is entering and leaving the building, proximity sensors record people being present at the location, and even temperature and lighting sensors can be used to detect human activities in the building. Such data can be a treasure trove for building applications that can be of great benefit to the building tenants. For example, heating, cooling, and air conditioning systems can take into account room occupancy to fine-tune their operation, making for a more comfortable environment with less energy waste. Or, applications can respond to price signals from the electric utilities to increase or decrease the load on the system so as to reduce energy costs without sacrificing the tenant's comfort. But again, these sensors directly or indirectly monitor aspects of human behavior. This information may show where people spend their time and who they interact with. This information is definitely private and should be treated as such. Building tenants could be okay with an application gathering anonymized occupancy data to set the heating and cooling systems properly. But they would probably object to their behavior in the building being monitored all the time. Do existing IoT management systems handle such cases? A third, but not final use case is a city that monitors traffic via IoT devices. My city has deployed a traffic management infrastructure to monitor and alleviate congestion. This consists of a large number of sensors spread around the city generating tons of data. For example, cameras or other types of roadside sensors can monitor the identity of vehicles passing by to detect violations, whether vehicles are jammed to intersections or blocking emergency lanes, or just the average speed of vehicles at each junction. Such infrastructure can be used to manage traffic in many different ways, possibly by developing different applications reusing parts of the same basic data. For example, an application could manage traffic light patterns to alleviate traffic by providing more opportunities to clear a congested road. Another application could manage city buses, looking at their location and the conditions ahead to more accurately estimate their arrivals. And there are many other possibilities that have actually been deployed in real cities. Still, data gathering can always cause privacy issues, especially when individual vehicles and their drivers are identified. Drivers would not want their routes to be visible to everyone. And while the law may allow or even require the city to check vehicle speeds and identify offenders, such privacy violations should be limited and legal. The city should not allow applications to create private profiles by correlating vehicle movements across different roadside units. Can current city traffic management systems make such guarantees? The rationale behind SeEDS was to offer a solution to people and companies that are dealing with these exact problems. So, what is the common pattern across these examples? On the one hand, they all concern entities who gather lots of sensitive data. Not all of this data may be sensitive directly, but they can become sensitive if they are combined and processed with other data to create user profiles. In the examples that we show, such data came from wearable devices, from building infrastructure, or from roadside sensors. Now, as long as these systems serve a single purpose, they can be designed and programmed to operate as intended. But when tons of data are generated, there is always the temptation to reuse them. Indeed, many local and state governments around the world are actively working to open their data to third parties for the development of new applications. And as we saw, when data are shared with different applications, they have different goals and privacy issues arise. How do we know then that our data is not misused? What SeEDS is offering is a solution to this exact problem, a way to store private data to untrusted cloud infrastructures in the sense that users agreeing to share their data should not blindly trust whoever gathers their data to safeguard their legitimate interests. SeEDS allows data to be always stored encrypted in the cloud, which means that nobody can use their data without the user's consent. Furthermore, SeEDS allows users to choose what to reveal from their data and to whom by incorporating a decentralized security and privacy solution with strong guarantees on data authenticity. Finally, SeEDS is an open source solution based on other open source projects and standards-based specification, preventing the entities and users relying on SeEDS from getting locked into a proprietary system that takes away their control over their data. But what is SeEDS and how does it offer such benefits? Let's see what SeEDS is all about. As we already mentioned, SeEDS stands for Secure and Efficient Data Spaces. In a nutshell, we can describe it as an implementation of the data spaces concept over NDN. The data spaces concept comes from ETSI, the European Telecommunication Standards Institute, and it is what we have adopted as the application layer of SeEDS, that is, the path of SeEDS that applications can exploit. Data spaces is an abstraction of storage, so a data space is basically a collection of data, most likely stored in some cloud servers. Data spaces, however, do not specify how storage is implemented. It can be a centralized database or a distributed cloud-based system. What data spaces do specify is an application programming interface, or API, that tells your application what kind of queries it can make to retrieve data from the data space. As we will see, this API is quite rich in the sense that it provides very powerful options for retrieving the data you want. The goal behind standardizing such an API is to allow different storage providers to offer the same API, allowing data to be moved from provider to provider without changing the applications using them. Of course, even though data spaces do not tell you how data are stored, they assume that the data in a data space are a collection of data items or objects which look like JSON-LD records. JSON-LD stands for JSONs for linked data, and it is a way to represent to the application data items consisting of a set of named attributes, each of which can have a value or be composed of other attributes in a human-readable form. So even if the data inside the data space are stored in an SQL database, for the API they look like JSON-LD items. We will say more about JSON-LD in the technical part of this webinar. The other component of SeEDS is Named Data Networking, or NDN, which is the network layer technology over which we are implementing data spaces. NDN is a content-based networking architecture, sometimes also called an Information-Centric Network, or ICN, meaning that it is a network built to exchange named data content items. This is in contrast to the Internet, which is built to exchange anonymous datagrams between IP endpoints. As in NDN, data items are individually named, the network can retrieve them from wherever they may be available, including caches and replicas of their origin servers, thus implementing multi-homing of data. In addition, when many clients ask for the same piece of data, NDN can merge these requests and serve them via multicasting. We will also say more about NDN in the technical part of the webinar. The reason that SeEDS combines data spaces with NDN is to offer the flexibility of data spaces with the efficiency and reliability of NDN. But why are data spaces flexible? Well, nearly every type of data set can be modeled as a set of content items. Data spaces only mandate that each content item must have a unique identifier or ID to separate it from all other items in the data space, and a type which can be common among many content items. For example, a roadside unit sending information on passing vehicles to a data space can generate a unique ID, which could be a timestamp or a sequence number for each vehicle record, and use as the type of vehicle, for example, passenger car, truck, motorcycle, or bicycle. Each such record can also have any number of attributes with a value for each attribute, as defined by context, which is a description of what the items for a specific application using this data space will look like. To actually look up content items, an application uses the NGI API, which is an API that defines what queries look like. At its most basic, a query can ask for a specific item by specifying its ID, or ask for a collection of items by specifying their type. Both types of queries can also include filters on their attributes, which can have two different forms. First, the query can ask for only some of the attributes of each item to be returned. For example, we can ask only for the speed of passing trucks. Second, the query can specify criteria that need to be met by some attributes. For example, we can ask only for trucks that have a speed of more than 50 miles per hour. We can also make temporal queries when data include timestamps, asking only for content items generated at a specific period of time. And finally, we can subscribe to events. That is, we can ask to be notified when data items show up that meet specific criteria. For example, whenever a vehicle is moving at more than 80 miles per hour. The implementation of the data space is responsible for parsing these queries and returning the appropriate data items. The other component of SeEDS is NDN. NDN helps make our implementation efficient. As we already mentioned, since in NDN data items are individually named, we do not need to ask them from a specific server as we do on the web, but we can ask the network instead to get them from wherever they may be stored. This can include replicas of the content and even caches, which means that NDN basically acts as an implementation of a content distribution network or CDN without requiring any application layer code, DNS redirections, or load balancers as the web does. We also mentioned that NDN can automatically merge requests for the same content item, if of course they coincide in time, and serve all requests together in multicast mode, which saves considerable bandwidth. A final touch that we're implementing on top of NDN is the migration of content filters inside the NDN network to reduce traffic. What that means is that when we ask for some data following a filter on their attributes, instead of first gathering up all data to one place and then filtering them out, we can send the filters to the network nodes that have matching data, perform the filtering there, and only have the filter content items returned to the requester, thus potentially saving tons of traffic. Another area where SeEDS adds to what NDN and data spaces can do is support for reliability during failure situations. Existing data space implementations are basically centralized using a single data broker to receive queries, parse them, gather the data, and return them. In our implementation, however, we use multiple servers called content registries to manage the data space. In addition, we implement primary-secondary replication of these registries to ensure that they are always available. And of course, since data can be replicated or cached in NDN, it is much harder for the data items themselves to become unavailable. Finally, SeEDS places specific emphasis on securing its data space implementation and maintaining the privacy of the users and their data. SeEDS implements a comprehensive security system. It is based on centralized identifiers or DIDs, which are cryptographic identities that users can generate by themselves as often as they like. Applications can build complex security models based on the DIDs of the content producers and the content consumers. Our implementation can add the DIDs of the various stakeholders inside the actual network packets, allowing fully decentralized authentication and integrity checking. We also exploit verifiable credentials or VCs for access control. VCs are cryptographic documents generated by content owners authorizing other ends in the system, identified by their DIDs, to distribute or access their content. Again, VCs can be included in network packets. As a result, SeEDS does not require a PKI to be set up or paid for, and it does not rely on any centralized elements to maintain security. In the privacy area, SeEDS has implemented a cryptographic solution for selective content revelation. This means that a content item consisting of a large number of attributes can be signed only once by its creator with a signature creating the entire content. But then, authorized SeEDS entities can reveal only some of the attributes of the content requesters, possibly due to access control restrictions, without having the creator sign the item again. Our scheme can still prove to the requester that the visible attributes are indeed part of the original signed item. For example, a roadside unit can sign vehicle records only once, and SeEDS can allow the police to actually see the license plates of speeding vehicles, but traffic management applications to only see the speed of the vehicles. Both applications know that the roadside unit generated the data, but there is no need for the roadside unit to sign a different version of the content item for each conceivable application, thus allowing reuse of data without overloading data creators. So far, we have talked about what SeEDS offers, but there are other implementations of data spaces, so the question is, why should one choose SeEDS to build a data space? Or why should a funding organization provide support for the development of SeEDS? First, let us look at the economic benefits of SeEDS. SeEDS is a fully open source implementation that anyone can use, based on the open source implementation of NDN, as well as other open source libraries. Open source means that there is no proprietary code that cannot be audited or taken out of the market. Everyone can reuse and extend it. It also means that there can be no vendor lock-in, causing high maintenance fees down the road after an organization has heavily invested in developing its data spaces. And it's not just the implementation that is open. The NGSI API implemented by SeEDS is also open and controlled by a standard-setting organization, meaning long-term stability and availability of data space solutions. If SeEDS does not serve an organization's needs anymore, it can migrate to another data space implementations without rewriting the applications using the NGSI LD API. And the same applies to security architecture, which is built on international standards for DIDs and VCs. The SeEDS implementation is also distributed, both in terms of having multiple servers implementing the data brokering service and in terms of replicating its servers. Coupled with the native ability of NDN to get content from different origins and broadcasts, this means that SeEDS does not have single points of failure that can bring down an organization's application and disrupt its businesses. Finally, SeEDS relies on decentralized security architecture. As a result, it does not require organizations to set up a PKI infrastructure or pay certification authorities for key certificates, so security is both cheaper and more efficient. Adopting SeEDS also comes with environmental benefits, which are of interest to both funding organizations and potential adopters. Currently, content distribution via CDNs can be extremely inefficient. It relies on data generated from edge devices like wearables, roadside units, and IoT sensors, ending up at cloud servers possibly located across the globe. Then, applications need to pull this data from storage servers to appropriate application servers, possibly located at other cloud servers, before eventually getting the results to the users. This leads to a lot of data crossing the internet multiple times. The goal of SeEDS is to move as much processing as possible inside the network, and this is why we chose the data spaces approach and the NDN underlay. The NGSI LD API is very expressive, allowing very complex queries to be formulated and passed to the data space implementation, including filtering constraints. Our SeEDS implementation can then move these filters closer to the origin of the actual data items, allowing only the filtered data to be returned to the users, rather than getting everything to the user or the application server and filtering it locally. NDN, on the other hand, allows data to be accessed from wherever they are available, thus allowing the closest copies to be used without having application layer code managing content distribution. And when data need to be moved around, they can exploit multicasting to reduce their traffic impact, something especially useful when replicating data to multiple servers for reliability purposes. The end result is that fewer data need to be moved at smaller distances. Finally, the adoption of SeEDS has a social impact as well. It is no accident that data spaces were proposed by ETSI, a European organization. The goal was liberating data from silos. Currently, tons of data are locked inside proprietary application platforms and stored in public or private clouds with little or no protection. Data spaces attempt to make data sets portable by using a standard data access interface over each vendor's data broker implementation. This allows the creators and owners of these data sets to have control over their data, moving them to providers that meet their performance, security, privacy, and reliability requirements. Furthermore, SeEDS is especially focused on security and privacy. Starting from the content-based security of NDN, which allows individual pieces of content to be authenticated rather than the server storing them, SeEDS adds DIDs and VCs to provide a distributed scheme that can operate both on a hop-by-hop basis, preventing fake data from wasting network resources, and on an end-to-end basis, allowing applications to make strong security assumptions. In addition, the selective content revelation scheme of SeEDS allows all data to be signed at its origin, which can be either an IoT device or a gateway trusted by the device's owner and be reused in partial form without resigning it, allowing different applications to be built on top of the same data sets without burdening the content creators with more signing duties. Finally, our decentralized security solution based on DIDs and VCs is a stepping stone towards internet evolution to a more secure network. It allows different security schemes to be built depending on application needs without requiring expensive and centralized PKIs to be built or rented, thus increasing reliability and enhancing efficiency. It is now time to move to the second part of the webinar, which delves into the details of how SeEDS works internally. To understand how SeEDS operates, you need to have a basic understanding of data spaces and NDN, as these are the basic components of our solution. If you know about this, you can skip the next few slides. If not, we will start with an overview of data spaces. As we said before, data spaces are an abstraction of storage in the cloud. It is a collection of technologies that allow interoperation between storage users and storage providers, allowing data to be stored securely in the cloud. In a data space, we have three basic entities. The context broker mediates between the content provider and the content consumer, providing a standardized API that allows application and storage to talk to each other regardless of their specific implementations. The context broker essentially hides the cloud storage behind the standardized interface. This is what we are actually implementing in SeEDS. The content provider is the entity that creates content for storage in the cloud. It can create, update, and delete data items by talking to the context broker. The content consumer is the entity that consumes the stored data to implement an application. It can read data directly, make complex queries to filter data sets, or subscribe to specific events related to data. As we mentioned in the overview of the project, the data stored in a data space can be considered as a set of content items using the JSON-LD content format. This does not mean that data have to be stored in this format inside the data space. They can be stored in an SQL or NoSQL database or any other kind of form or service. But for the purpose of the NGI LD API, which is used to communicate with the outside world, we can view each item as a human-readable JSON-LD object. These items consist of a set of name attributes and their values. All items need to have an attribute called ID with a unique value in the data space. They also need to have an attribute called type that will most likely have the same value for many different content items. All the other attributes must have a name and a value. It is also possible to have compound attributes consisting of simpler objects. Although content items can have any attributes desired by an application, these have to be described in a context. The context lists the different attribute names. Each content type needs to have its own context to ensure that all items of the same type have the same attributes. The NGI LD API supported by the data spaces is what makes data spaces independent of the underlying storage implementation, by offering a standardized way to query the data space for content items with specific properties. The first type of query is asking for an item based on its identifier. Since identifiers are unique, this can only return a single item. However, the query can only ask for a subset for the attributes of the content item. As we mentioned before, this may be because a specific client may only be allowed to see some of the attributes for that content item. The second type of query is asking for all items of a specific type, which returns a set of items. Again, we can only ask for some of the attributes of these items, either because we only need some of them or because we are only allowed to see some of them. Both by ID and by type queries can include filters on the attributes, that is, criteria that need to be met for an item to be returned. This is normally used with by type queries to limit the number of items returned. For example, we may ask only for content items related to vehicles that had a specific speed or were moving at more than the speed limit. Another option provided by the API is temporal queries, which allow query to return past versions of mutable content items, that is, items that can change over time, such as the speed and location of an individual vehicle. For a temporal query, the content consumer emits a request for a content ID or type, adding a time reference regarding the content's creation and some additional parameters. Specifically, the consumer specifies the number of versions desired, a timestamp, and the condition before or after. For example, 5 versions after 12 o'clock at January 1st, 2025, or 1 version before now, which implies the latest version. Finally, consumers may subscribe to get notifications that the requested content item has become available. To receive a notification, a consumer must send a subscription for a specific ID or type, possibly with some content filters included. SeEDS is not the first implementation of the data spaces concept. So why should you use SeEDS? Well, it improves upon existing implementations in multiple ways. First, previous implementations had a single entity in the role of the broker, translating between the NGSI API queries and whatever storage implementation was hidden behind the broker. This makes the broker a single point of failure, as if it fails, there is no access to the data. In addition, a centralized broker raises scalability issues when the number of queries and their complexity grow. Second, existing data space implementations expect the broker to manipulate data in order to provide operations as simple as returning a subset of the attributes of a content item. The problem with this is that the content item returned by the broker is not the same as the one generated by the content producer. So even if the content producer did sign the original item, the content item returned does not match the signature. As a result, in secure applications, the consumers must trust the content broker. Third, as end-to-end encryption has become the norm in the web, with nearly all sites implementing HTTPS, when queries are made that refer to the same item, something that can happen when there are multiple subscriptions to the same event, they cannot be bundled together. Instead, each query must establish a separate unicast connection. This also prevents caching, as caches cannot understand what is happening inside an encrypted connection. The SeEDS implementation improves upon existing solutions in all these areas. First, by using an ICN architecture, specifically NDN, it can implement many of the operations required by NGSI LD inside the network itself, rather than gathering all data close to a request and then processing it. Second, SeEDS uses a distributed architecture for the brokers, with content items spread across many brokers for scalability and primary-secondary replication to ensure that no broker goes off the air for long. Finally, SeEDS implements security solutions that focus on data rather than connections, allowing multicast and caching to coexist with strong encryption as we encrypt and sign the content items themselves.
So NDN, or Named Data Networking, is the second aspect of SeEDS that some of you may not be familiar with. So let's go ahead and say a few words about NDN. NDN is an information-centric network architecture, which means that the network exchanges named data items. This is in contrast to IP datagrams that have source and destination IP addresses, but are anonymous. NDN reflects how content distribution operates. Users want to access pieces of information, not servers, but HTTP requires connecting to a server that holds the content before asking for the content itself. Content items in NDN have hierarchical names, which may or may not be human readable. In NDN, each endpoint can be both a publisher and a subscriber to named content items. To make content available to the network, a publisher announces or advertises a content prefix, for example, /AUEB/MMLab, and this essentially means that the publisher can provide any content whose name starts with /AUEB/MMLab. This information propagates in the NDN network using a routing protocol, and when an endpoint wants to retrieve a piece of content, it sends an interest containing the identifier of the desired content, that is its name, and using routing information created by the content advertisement process, the interest is directed to the source or the publisher of the content. Many sources for the same content can advertise the same content prefixes, and also the content can be found cached all the way to the content provider. When a content provider or a cache receives an interest message, it sends back the content requested in a data message. This does not require routing because when interests propagate towards a publisher, they leave behind breadcrumbs. The data message follows these breadcrumbs all the way back to the content provider. If multiple interest messages for the same content are sent close in time, then their breadcrumbs are merged when they converge at the network node. This allows a single data message to be issued by the content provider, branching out when the breadcrumbs diverge, essentially offering native content multicast. So why did we select NDN as the basis upon which SeEDS implements data spaces? Well, there are many reasons, and some of which will become apparent as we describe our design. But some of them should be fairly obvious already. Well, first, NDN, by securing content items rather than connections, allows forwarded content items to be opportunistically cached in the network, leading to lower response times and reduced network traffic. Second, by aggregating interests issued at the same period of time, it allows content to be delivered via multicast, reducing traffic, especially closer to the origin servers of popular content. This can be very useful for subscriptions to popular content which will be served via multicast when content appears. And finally, NDN allows the same content to be served from multiple network locations by simply advertising the same prefixes from all replicas of an origin server, meaning that we can have native multi-sourcing, something performed at the application layer in CDNs with considerable complexity.
We now turn to the details of the SeEDS implementation. We will first explain how different types of queries are handled, ignoring security and privacy for the moment, and then present our security solution later on. Let us start with an overview of what the SeEDS implementation of a data space looks like. The data space itself is a set of NDN nodes interconnected in any topology desired, forming a network cloud. Each content consumer and content provider connects to a SeEDS proxy or just proxy. The job of the proxy is to mediate between the content providers and consumers in the data space, translating between HTTP and NDN. A proxy is a server at the edge of this NDN cloud where the clients can connect. The proxy receives NGI and NGSI-LD API messages from external endpoints over HTTP and translates them into NDN messages. When it receives the NDN responses, it turns them back into HTTP messages and returns them to the requesting endpoint. As a result, the endpoints have no idea that the data space is actually internally using NDN. Some NDN nodes, in addition to performing regular NDN operations, like routing and forwarding, may act as registries for content. A registry can be any NDN node, either at the border of the network or inside the network. For each content type in a data space, there is a registry which tracks all the items for this specific type. Note that the registry does not store the data. The data can be stored anywhere in the NDN cloud. The registry just stores pointers to the item for the type, allowing them to be located when a query for a type appears. To see how NDN handles NGSI-LD API requests, the simplest example is the query by ID, which must return the unique item with the identifier specified in the request. We first need to explain how an item is stored in the data space to see what state is created and how it is used later for its retrieval. To store a content item, a content provider sends an HTTP POST message to its proxy containing the content item itself in JSON LD format. The SeEDS proxy can store the item locally and announce the unique identifier of the item to the NDN network. Essentially, the identifier is the name of the item. Alternatively, it can send the item to another SeEDS node, which will store it and announce the identifier. When a consumer wants to get an item with a known ID, it also sends an HTTP message, but it is a GET message this time. This message is sent to the SDS SeEDS proxy and it contains the unique ID of the item. The proxy of the consumer simply creates an NDN interest message for the content item with that name and propagates it inside the SeEDS network. This message will eventually reach the node storing the content, which may be a cache of course, and send back with the data message to the requesting proxy, who will then create an HTTP response message to return the content item to the consumer. This does not seem that complicated. It is actually a straightforward use of NDN. Since each content item has a unique ID, we can just use this ID as the content name for NDN. It's a simple name translation. But actually, even in this simple case, we stand to gain a lot from using NDN. First, if a content item is cached, which it may very well be if it was previously returned for another request, it can be returned from the cache rather than from the server permanently storing it, the origin server, saving time and energy. Second, the item may be replicated to multiple origin servers, the same way CDNs propagate content to different clouds to reduce response time. NDN will just route the interest to the nearest available location, saving time and reducing the possibility of content unavailability due to a server failure. Third, if multiple consumers ask for the same content, they will all be served via multicast, thus reducing network traffic. This is more likely to occur with subscriptions referring to the same content. The only problem is that we cannot use this same method for requests by type, as many items have the same type, meaning that we cannot turn the type into a name. One could propose using the type as a name prefix and the identifier as the name suffix, but this would prevent us from finding content by ID. We need a different solution, which is having a server act as a rendezvous point, or RV, for each type. Let us revisit content creation to also incorporate types. We will not change the request by ID, but we will add some more steps to the procedure to also allow by type requests. As these are more complex, we will use message sequence charts to explain each step of the process. First, we need to assign an RV for each type of content. Since each type has a defined context, types are known to the data space, so we can have a static assignment of types to nodes acting as RVs. Another possibility is to use hashing to assign types to nodes as in distributed hash tables. Whatever the method of assigning RVs to types is, we only need to assume that the node acting as an RV for a specific type knows that. The other nodes will find out about that RV using NDN. So when an RV is assigned a new type to handle, it announces the name of the type to the NDN network. For example, if the type is called car, the RV for the type will advertise the name /car to the NDN network. When a content provider sends an HTTP post message with a new content item to its closest proxy, the proxy will look at the item and advertise its name to support by ID queries, as we explained before. Now say that the item identifier is car1, then the proxy will advertise the name car1, but it will also look inside the item to find its type. If the type is car, then the proxy will issue an interest for the name /car/car1. That is, it will use the item's type as the name prefix and the item's ID as the suffix. This interest will be routed towards the RV for type car, as this RV has advertised the name /car. When the RV for the type car receives the interest, it makes a note that a new item of type car with the ID car1 has appeared by adding the name /car1 to its database for type car. Essentially, the RV maintains a list of pointers to names for the type. Note that these are pointers to names, not locations, allowing content to move in the network without changing its name. The RV will then return a data message to the proxy, basically acknowledging that the pointer to the item has been stored. At this point, the SeEDS proxy can respond to the content provider that the item has been properly stored in the data space. Now let us see how we can get the items of a specific type. As before, we start with an HTTP GET message from a consumer to its SeEDS proxy containing a by type request. Say that it asks for items of type car. The proxy translates this into an interest for /car to ensure that it will reach the RV point for the type who has advertised this name. When the RV for type car gets this interest, it retrieves from its registry file all the IDs for that type and returns them in a data message to the requesting proxy. At this stage, the proxy can look inside the response and find the identifiers of all content items for the type, so it can just issue interest for each content item by ID. This is exactly the same as a by ID request. It is just that there can be many of them. When the items arrive, the proxy can package them and create HTTP responses, which are then returned to the consumer. This is it. The way we treat by type requests is basically a creative use of NDN names. We assign its type to an RV, and by the way, many types may be handled by the same RV. This RV uses NDN messages to keep track of all content items for this type. Again, note that the RV only stores pointers, not the content items themselves. These are located via the identifier of the item as usual. The main benefit from NDN is that storing pointers rather than the content itself. This means that we can get the content items from many different places, including replica servers for the content or caches, something not possible in other data space implementations. And of course, in each individual GET by ID request, we have the benefits previously described due to NDN. The next issue is how to handle subscriptions to content. The problem here is that subscription refers to content that's not available yet. If it was available, it would be a simple request like the ones we saw. How can we ask for something that does not exist? Well, we will use the RV idea to track subscriptions as explained next. The problem with subscriptions is that they need to be stored somewhere until a content item that matches the subscription appears. But how do we know when the subscription has a match? We reuse the idea of the RV that we introduced for types by adding RVs for subscriptions that can be easily located when the right items appear. When that happens, the RVs notify the subscribers about the matching item. The subscriber can then use the regular get primitives that we have already designed. As a result, after the notification part, we simply reuse the existing signaling to get the matching items. Now, where do we place the subscription RVs? For subscriptions to types, that is, subscriptions that wait until an item with the right type appears, we can just reuse the same RVs that we already defined to maintain the type registries. These RVs are already notified when new content items with the type they are handling appear in order to update their database. They are thus an obvious choice for storing subscriptions to the type. For subscription to IDs, we do not have existing RVs, as locating these items can be directly performed by NDN without intermediaries. We therefore need to assign an RV to each subscription depending on its ID. To choose an RV, we reuse the idea of determining the RV for each type by hashing the type. In our case, we hash the identifier include the subscription and map its range of identifiers to a specific RV exactly as in a distributed hash table. We will first explain how subscriptions by type work, since we have already seen the role of the RV nodes for get by type requests. The subscription starts with the content consumer sending an HTTP post message to its proxy containing the subscription request and the desired type. The proxy then sends an interest message for the type with the subscription option. For example, if the subscription was to type car, the interest will be for the name /car, / the name of the proxy issuing the subscription. This will be naturally routed to the RV for type car as a regular GET request, but since it's a subscription, it will be stored in the RV along with the name of the proxy that sent the subscription. The RV will then return a data message acknowledging the subscription. At some later time, a new item may appear for type car. As usual, content item creation also means that the RV maintaining the registry for the type is notified. When that happens, the RV sees that subscription has been matched by an item. It will then send an interest to the proxy that sent the subscription, using as a prefix the name of the proxy and as a suffix the name of the type. The proxy thus learns that subscription for the type was satisfied. It can now finally proceed as in a regular request by type, which means asking for the type registry and then asking for the IDs contained in the registry. For subscriptions to IDs, we also start with an HTTP post message. This message comes from the consumer and contains a desired identifier, say ID1. Now we assume that the dataspace has assigned via hashing each possible ID range to a specific RV that has advertised the name for this purpose, for example, /scope1. So when the proxy receives a subscription for ID1, it maps the ID to scope1 and sends an interest to /scope1/ID1 / the name of the proxy as in a type subscription. This message is eventually received by the right RV, say RV ID, which stores the identifier desired in the proxy that asked for it, sending a data message as an acknowledgement. When the content with the right identifier appears, the creator of the item also notifies the RV for the item, RV ID, to satisfy any pending subscriptions. The RV node sees that there is a subscription for ID1, so it sends an interest with the prefix, the name of the proxy subscribed to the event, and as a suffix, the name of the content, which is ID1. And since the proxy now knows that the content with identifier ID1 has appeared, it can proceed with a regular get by ID request to retrieve it. A final issue is how SeEDS manages to avoid single points of failure. We have seen that there are RV nodes for each type and subscription to the type, and RV nodes for each range of IDs. If such a node fails, we can no longer find the appropriate content. To prevent these problems, we have decided to implement a simple primary-secondary backup mechanism for each SeEDS server that should not be a single point of failure. To achieve this, each node offering a SeEDS service needs to have one or more backup servers to take over the tasks if it fails. We will assume for simplicity that there is a systematic way to do this mapping or a tight assignment of backups to primaries. Also for simplicity, we will assume that there is a single secondary for each primary. For our scheme to work, each primary SeEDS server announces two names in the NDN network. the name state plus its ID, which is used to replicate its state to the secondaries, and the name is alive plus its ID, which is used by the secondary to detect that the primary has failed and that it needs to take over. So every primary server advertises these two unique names when it starts operating. Each secondary in turn periodically polls these two names. It sends an interest message to each one and expects a data message as a response. Its next actions depend on the contents of the data message or its absence. As we already said, the primary announces a unique name for itself for state backup, for example, /state server1, and another name for failover, for example, /is-alive server1, which are both known by the secondary. Periodically, the secondary sends an interest to /state server1 /hash, where the hash is a hash over its current version of the primary state. When the primary receives this message, it looks up in its log to see which version of its state the hash corresponds to. Then it responds with a data message containing a patch to update the secondary to its current state, along with the hash of the resulting state. The secondary, on reception of the data message, updates its state with a patch and checks the hash. In case of a complete loss of synchronization, the primary can always send its entire state from scratch. So this takes care of state updates. For failover to work, the secondary server periodically sends an interest to /is-alive server1 plus a nonce, that is, a random value that has not been recently reused. If the primary does not respond with the data message including the nonce within a reasonable time, the secondary determines that the primary has failed and takes over by announcing all the names the primary was announcing before. So this takes care of failover situations. There are a few more things to add here. First, in state updates, the default is to only send updates rather than the entire state of the primary. To achieve this, the secondary sends a hash of the state it has to uniquely identify to the primary what it already has stored. This allows the primary to send a patch to update the secondary state. The reason for adding the patch as a suffix to the state name is to allow patches to be cached. If we have multiple secondary servers, whenever one of them asks the primary for state updates, it uniquely identifies its own state via the hash. If a response to this state is cached somewhere in the network, it can also be used to update the state of other secondaries. Plus, if many of them ask for the same state simultaneously, they are served via multicast. Second, in the keep alive messages, we said that a random nonce is added to the name. This is used to suppress cast responses. Unlike in state messages where we want to reuse cast responses, in keep alive messages we want to ensure that the response is fresh and comes from the primary. If no response is received on time, then the primary must have failed. In case of multiple secondaries, an election protocol is needed to select a new primary. We do not focus on this, but since secondaries are assigned in advance, a simple election algorithm can be used. The last part of the implementation is an overview of how SeEDS enhances the privacy of the users and their data via the selective revelation mechanism that we talked about in the first part of the webinar. We will not describe the entire security architecture, as explaining what DIDs and VCs do would take a long time, and SeEDS actually follows previous projects in how it used them to create a distributed security infrastructure. Selective revelation, on the other hand, is something that fits very well with data spaces, as we will see. Now, what is the problem we are trying to solve, and why is it important? One of the goals of data spaces is to allow data to be reused by different applications, but each application may only need a subset of its content item, or may only be allowed to see a subset of a content item. Recall the example of roadside units gathering information on passing vehicles. The police is by law allowed to see even some private attributes of the generated content items, but traffic management applications should not see them. We can then state our problem as follows. We want the data space to store the entire content items generated by producer, which are originally signed by the producer for everyone. On the other hand, we do not want content consumers to have access to some of the attributes. Different consumers may see different subsets of each item. We also want attribute hiding to be implemented by the broker in the data space, which has ample processing power, rather than having the content producer, which can be a simple IoT device, producing different versions of the item and assigning each one of them separately. Finally, we want the consumer to only trust the content producer, not the data broker. So we basically want the data space to produce the subsets of the content items, but still allow consumers to verify the integrity of an item, even though they can only see part of it. This is what we mean when we talk about selective content revelation. We will show two different signing solutions that solve this problem for SeEDS. A core concept behind our solution is a disclosure. A disclosure is basically an attribute that may or may not be visible to a specific consumer. Our solution turns its attribute to a disclosure, where the name of the disclosure is the JSON pointer of the attribute, basically its hierarchical name, and the value of the disclosure is, well, the value of the attribute. To implement our scheme, then, we decompose each item into a list of disclosures and sign them in a specific way. Then, when we want to return an item to a consumer, we reconstruct a partial item by only including the appropriate disclosures plus enough information to prove that the disclosures are authentic. Essentially, we want the consumer to verify that the partial item is an untampered with subset of the original item as created by the producer. The first step of this process is decomposing an item to its attributes. As an example, the JSON LD item on the left side of the figure can be decomposed to the list of disclosures in the right side of the figure. If an attribute is a composite one, that is, it consists of sub-attributes, for example the brand, which consists of a company and the model, each sub-attribute becomes a separate disclosure. Note that the disclosures have hierarchical names, which show how each attribute is related to the original item. On the other hand, when we want to reveal some of the disclosures, we repeat the previous process in reverse. We take each disclosure to be revealed and place it in the appropriate place in a new JSON LD item. In the example of this figure, we only reveal the attributes in green from the item list on the left side, creating the new JSON LD item on the right side. The question is how to persuade the consumer that the new item is indeed an untampered with subject of the original. We will only show in detail the first solution that we have implemented, which is the hash signature-based approach. In this approach, to sign a created item, we start by generating a random salt value for each disclosure. We then hash each disclosure along with its salt value, and then we digitally sign the concatenation of all these hashes. Inside the data space, we store the signature over the entire item, all the hashes, all the disclosures, and all the salt values. When we want to include some of the attributes in a new partial item, we reveal the corresponding disclosures along with their salt values. However, for the hidden attributes, we only reveal the hash value. Finally, we reveal the signature over the entire item. In the example in the figure, we only reveal the green attributes, so we provide their content and salt value, but for the other attributes, only their hash. Before explaining how verification works, we can explain why the salt values are needed. In a large data collection, many items are bound to have the same values in some attributes. Since we are revealing the hash of the hidden attributes, an attacker could match the hash from a hidden disclosure with the content of another item for which the attribute is revealed, and then it can guess its content. The salt is used to make disclosures that are otherwise the same, for example cars with the same brand, to have a different hash. Finally, the verification phase is similar to signing. For each revealed attribute, we calculate the hash, including the salt. This we know. But we also know the hashes for all the hidden attributes. Therefore, we can recreate the list of hashes and verify that it matches the signature of the original item. We can then verify whether the partial item matches the signature of the original, even though we only know the hash of the hidden attributes, which due to the salt values are even more random. We have also designed a more complex signing scheme for selective revelation, which is based on BBS plus signatures. BBS plus signatures allow a signer to sign a group of messages, and then a third party can select a subset of these messages that should be revealed to someone else. The third party then creates a zero knowledge proof, or ZKP, that shows that the messages revealed are authentic. This means that these messages are part of the original set that provided the signature. The size of this zero knowledge proof is linear on the number of hidden messages, so it is smaller when we reveal nearly everything and larger when we reveal nearly nothing. We can very simply apply BBS plus signatures to our data spaces. We just treat this disclosure as a message, sign the group, and then ask the broker to calculate a zero knowledge proof that shows that the revealed disclosures are part of the original item. We will not go into the details of the advantage and disadvantage of each of these two schemes, but BBS plus signatures do have some advantage over the hash scheme that can justify their extra computational cost. We have reached the end of the webinar, so we will close with a roadmap of the SeEDS implementation as of July 2025. We completed the initial SeEDS implementation in June 2025. This implementation includes the entire NGSI LD API, including subscriptions and filters. The next stage of our work is testing our implementations both in our lab and the servers of the worldwide NDN testbed. Our goal is to test the performance of SeEDS, its reliability when servers fail or are attacked, and finally its compatibility with the NDN software, which have not modified in any way. This will take place from July 2025 to September 2025. Finally, we expect the full SeEDS implementation to be complete by October 2025, adding the solutions for distributed intermediaries in the form of primary-secondary backup, as well as security and privacy schemes. That was a long presentation, and I hope we did not tire you. If you want to find out more about SeEDS, you can look up the project site hosted at the MM Lab, where you can find more detailed documentation, project papers, and other project presentations. Thank you for your time and patience.